So now we will talk about the next lecture, which will speak about the other varieties of loads which are acting on marine structures. So far we have discussed about hydrodynamic loading, and aerodynamic. So we have seen different applications where which spectrum can be used appropriately, what kind of structure. Now ice loads are predominantly important in Arctic regions. There are different varieties of ice conditions that can cause loading. One is what we call as a level ice, other is broken ice, ice ridges, and of course icebergs. They are responsible for causing impact loads on marine structures. Now let us quickly see what are the effects that ice can cause or ice load can cause on marine structures. It can result in creep, cracking, buckling, spalling, and crushing. These are different consequences what ice loads can cause to the marine structures. Interestingly, ice loads vary with space and time. They generally cause two kinds of effects on structures. One is what is called global, other is called local. The global effect is also called as total load in the literature. The local effect is also called as pressure load in the literature. Let us now look at the idealized time history of an ice load. I am talking about the level ice load. This is local. I also have another figure where I will talk about the total. So the loading, this is what we call the loading due to ice submerging and sliding. What does it mean is the ice load starts applying its maximum pressure at a very short instant of time, then the load is released. Then as the load is released, the ice starts sliding, and that is creating another kind of force. Of course, the magnitude of the sliding is much lesser than that of submergence. So this part is mainly due to submergence of ice, this part is mainly due to sliding of ice. If you look at the behavior in terms of its failure, then a similar curve is also existing. This is what we call as bending failure point. It is a maximum in terms of its loads, and this curve or this ascending line of the curve is related to crushing and bending together. It keeps on increasing. And this load is mainly due to turning of what we call ice flow. Turning of ice flow, this creates an additional load on the marine structures. This is about the local effects. Talk about the global effects. It is a random phenomena which varies with time as well as in space. Therefore, ice loads are imposed on marine structures as periodic load. They can cause failures like bending, crushing, and their effect on slender structures is very high. It means this increases the dynamic amplification factor. On, I should say, flexible structures. More interestingly, to quantify the ice load, people have done research. How this ice load can be quantified? While they did this work, they found out a very important parameter which governs the ice load. So, the most important parameter which governs the ice load is shape. Of the structure. If you look at the current codes, they include ice loads on extreme loads category, and they are considered as static ice loads. Okay, there is no dynamic effect in this. That is what the current codal provisions are. people have shown some interesting studies saying that loads on conical structures, I should say ice loads on conical structures, are far lesser than cylindrical ones. Reference can be Sanderson 1988, Ice Mechanics and Risks to Offshore Structures, London, Graham and Totman Limited. So, Sanderson showed from his studies that ice loads on conical structures are far lesser than that of cylindrical shaped structures. Now, one can say, what is the main reason for this kind of difference in behavior in the ice loads, which is shape dependent? It is mainly due to the fact that in case of well designed conical shape, I am putting an adjective here, well designed conical shape, the failure of the structure is shifted from crushing to bending. So, if you really wanted to design any structural system or any geometry to resist crushing, this has got two aspects. For example, to resist crushing, you require either a massive geometry, that is shape and size should be very large, so that the stresses are very less, so it is safe against crushing. The second requirement is the material characteristic, that is material resistant against crushing should be high. So, you should use a special kind of material. Both ways it is not possible, because massive geometry can decrease stresses, can be safe in crushing, but our structures are having large buoyancy reserve. So, large size will affect the buoyancy considerably, which will affect my whole kinematics of the system. So, I cannot afford to have a large geometry. I cannot also have a material characteristic which is having a very high strength in crushing, because my predominant load which is acting on an offshore structure or marine structure is not crushing. I always design it to be safe against bending. Okay. So, by creating a geometric shape which shifts my failure mode from crushing to bending, it is advisable. It is because of this reason you will see in Arctic region most of the structures or most of the elements of the structures will be trapezoidal, conical or pyramid shaped, because on these shapes you will see that the load is lower and the failure mode is shifted from crushing to bending, which has been studied and indicated by Sanderson. So in the literature you have got ice load spectrum, like we have got wave spectrum, wind spectrum. We have got ice load spectrum available in the literature, which is being used to compute ice loads on marine structures in Arctic region. Of course, this is applicable to narrow conical structure. I already said ice load depends on the shape of the structure. A this is T bar by F nu exponential call this as 1, whereas A and B are constants, A and B are constants, F naught is the force amplitude on the structure, F is the frequency at which this spectrum is plotted, okay. F is the frequency at which this spectrum is plotted because it is function of F. T bar is called ice period, which is given by LB by V. LB is called ice breaking length, of course V is the velocity with which the ice cubes or the icebergs move. In this argument F is of course the frequency at which the spectrum is plotted, LB is also given as KH, where H is called ice thickness and K of course is the ratio of ice breaking length to ice thickness. Which is usually a value between 4 to 10. So ice breaking length is approximately 4 times thickness of the ice to 10 times thickness of the ice. So, this spectrum was suggested by Liu in 2009. So, Liu X G Li or Oberle's Q UE 2009. Research on short term dynamic ice cases for ice resistant jacket platforms at Bohai Gulf marine structures. Now, Li et al. Also gave certain values of these parameters based on which you can plot the spectrum for this. He said A can be 10, B can be 5.47, alpha and beta 0.64, nu 3.5, delta 2.5 and F naught which is used. F naught is the force amplitude on the structure which is given by C sigma F H where C is again the constant depending upon the type of the structure. This is sigma, okay. Sigma F is called ice bending strength, which is generally taken as 0.7 megapascal. H of course is the ice thickness, D is the diameter of the ice cone, LC is called characteristic length. We call this equation number 2. Now, the characteristic length which is to be used in the spectrum is given by further another equation whereas E is the ice elastic modulus, which is taken as 0.5 gigapascal, and rho W of course the density of water. Equation number 3. So, all parameters I know, LC I know, constant of course depends on the type of the structure, F naught is known to me and the parameters are known to me. I can now plot the spectrum and get the ice load coming on marine structures. So, any questions here? The fourth kind of load which we will discuss will be the seismic loads. We have already seen that the seismic loads are significant in the bottom supported structures. They cause inertia effect on the structures and seismic loads are very common in marine structures because of two reasons. One, marine structures are massive, large in size, and of course I should say weight. 2, generally they are bottom supported. But interestingly, if you have a flexible structure, which is moved to the seabed, then also seismic loads can affect the structure. We will see that quickly in few minutes from now, how this can be influencing. So, not necessarily the structure need be bottom supported. If the structure is moved to the seabed, for example like a tension leg platform, still those structures can also be excited seriously by seismic loads, because we understand that both the conditions are violated in case of flexible structure. They are neither massive nor they are bottom supported. Even then these structures can be also excited very significantly by seismic loads. We will just discuss it after few minutes now in this lecture. Now the fundamental question asked is, what do actually seismic loads do on structures? What do they do? Because if we talk about wind loads, they create wind induced vibration. Talk about wave loads, they create a drag force and a lift force. If the structure is compliant, it again generates radiation forces and diffraction force because of the movement. The structure is stiff, it attracts more forces, therefore the stress concentration in the members become high because of these kind of lateral loads. Whereas earthquake loads are actually acting at the foundation where the structures are resting. Okay, they are not actually a lateral load directly on the structure, is it not? Whereas wind load wave load and ice load on impacts, let us say they are all direct loads on structures. They can come and hit the structure can feel the passage of these loads and they respond to this, whereas seismic loads are actually acting at the seabed where the structure is resting or founded. So what these structures can, or what these forces can do to the structures? Importantly, the seismic loads can cause vertical and horizontal vibrations to the structure. Essentially what does it do is, remember importantly, seismic loads are not forces, okay, they are not actually forces. What they actually do is they try to displace the structure, that is try to move the structure in vertical and horizontal, maybe in both the directions in horizontal. A typical time duration of a seismic load which acts on a marine structure is about 15 to 25 seconds, that is the time. So just now we saw that seismic loads can displace the structure in all the 3 principal degrees of freedom or principal axis, as a result of which the structure has the following consequences. What will happen to the structure? The structure will generate internal forces because of the additional, I should say, displacement, but I am calling this as forces due to earthquakes. Now one may interestingly ask me a question, sir, what are those parameters based on which seismic loads can be computed? So what are those parameters on which seismic loads are dependent? One, the nature of the mechanism which causes earthquake, that is very important. 2, wave propagation direction. 3, reflection of these waves. 4, deflection of the seabed. So these are the parameters which affect the seismic loads formation or seismic loads on a marine structure. What are said as severe consequences caused on marine structures due to earthquakes? What are severe consequences? Very critical. 1, inertia forces due to, I should say, x double dot g, which is nothing but the ground acceleration. 2, damping forces caused due to movement of water particles. So far you have been understanding that the damping is always an added advantage of reducing the response. Okay. One can always say the moment I have damping in a system, the response of the system, be it single degree, be it multi degree, we are not looking at the dynamics perspective of this course. The moment I introduce damping in a given system, I understand that response of the system is reduced. You can also think that the response structure is controlled. What we are not understanding or what we fail to ignore is that it is causing parallel damage to the structure in terms of material degradation, to stiffness reduction, 3 exerting or initiating failure modes which are otherwise not predominant. It will initiate special failure modes which are otherwise not predominantly seen in the structure. So, damping, though it reduces response in the outer profile of the structure, implicitly it is causing many negative aspects to the structure. So, earthquakes will introduce damping forces because of the movement of the water particle, which can cause damage to the marine structure. So, the literature say that seismic loads are effective only on bottom supported structures, but that is seen in almost all literature. You can refer to any standard literature which has been referred in the NPTEL website on this course for understanding the effect of seismic loads on fixed jacket structures. For example, I will take up an example here which talks about the effect of seismic loads on TLPs. Whereas TLP is a flexible structure, it is large in size but it is not massive because the members are pontoons and columns are hollow. It is large in size but it is not massive, and it is designed for excessive buoyancy. Weight is very low. I think we all agree that TLP has got a very specific special design phenomena where the weight is much lower than the buoyancy, is it not? That is why when you try to offload the structure in sea, because of the buoyancy the structure is pushed up. Just to hold it down you provide cables or tethers, that is why they are called tension legs. So, weight is much lower than the buoyancy. So, buoyancy is coming from the submerged volume, weight is low because it is hollow. Okay. So, as the weight is low it is not massive, M is not very high, M is W by G, it is not very high. Unlike fixed type structures or bottom supported structures, these are very light in weight and they are not supporting directly or they are not resting directly on seabed, they are taut moved. What do you mean by taut moved? There is the initial pretension given to the tendons, the initial pretension T naught is of a very high value, okay, it is a very high value, that is T naught never will become 0. What do you understand by this? The tethers will never slack, they will always be in tight mode, they will never slack. There is always initial tension given to this, okay, and that value is very high, is pretty high compared to the weight of the platform. That is the design phenomena of TLP actually. Okay. So, in such kind of structures how earthquake loads will become significant? That is a very interesting question because it is violating both the conditions. The structure is not resting on seabed, the structure is not massive, then how does seismic loads activate this kind of platforms? I mean where is the code, how do you define the spectrum, and how do you compute the forces, and how will you transfer the forces. Interestingly, look at the problem here. I have a structure which is supported by cables or tethers, and the earthquake is happening here, and this is the water body. So how this force is getting transferred to the superstructure? Of course these are in tension. I should say this is T naught plus delta T naught, this is also T naught plus delta T naught. Of course these are all column members, these are all pontoons, we already know them, etc. And of course you have all topside detail, which are all very common for any production, drilling and operational platform in a marine system. If I have a jacket structure, I can say the structural system is resting on the bed, therefore these members will be activated by the earthquake loads, and these members will transfer these forces to the superstructure, therefore it is important, I can understand that. Whereas in the system I have got earthquake loads here, there is a huge water body because complaint structures are defined or generally designed for depth exceeding 600 meters up to now presently 1500 meters, okay, the very large and very deep water body. Therefore it is seen physically that the water body or the water depth will try to dampen the effect of earthquake on the superstructure, that is a general phenomena what people have. So we will take an example very quickly in few minutes to explain how the forces are transferred to the superstructure, what is the spectrum being used. So interestingly, when this thought actually came to researchers' mind, why earthquakes on flexible structures become important. Okay, there was an earthquake in Gulf of Mexico approximately at 250 miles of western side of Anna Maria, Florida on 10th September 2006 at 14:56:07 universal time at the geometric location 26.34 north, 86.57 west, which is the epicenter of this earthquake. And interestingly, it is on the same location closer to this Mars TLP was located. So this incident, for example, it is not the only, this incident triggered off the researchers to find out actually what would be the effect or the consequence of such an earthquake on a platform like TLP for which this is not designed, because generally people have been thinking that if the structure is not bottom supported, if the structure is not stiff or rigid, earthquakes will not affect these kind of structures. That was the phenomenon actually, earlier people thought. So it is after this period or subsequently closer to this, maybe in early 2000 or late 90s, people started thinking what would be the effect of this on structures like this. So, the foremost idea which came to the researcher's mind is that the delta T naught, which is nothing but the dynamic tether tension variation, is one key parameter which gets affected by earthquake. The dynamic tether tension variation will change with respect to time, and one may wonder, say, what will happen if this changes? Interestingly, I am not talking about TLP dynamics here, you can look into the paper, give the reference later. Interestingly, if T naught changes, the stiffness coefficients of a TLP changes. If the stiffness coefficient of the TLP changes, the whole dynamic characteristic of TLP alters. So, interestingly, though the force not directly applied on to the system, it is applied only to the seabed where the tethers are anchored, still the delta T naught value, which is changing significantly under these forces, affect the response very badly. Now, one may wonder, so what would be that significance of this change? The result showed that delta T naught or the dynamic tether tension variation changes to the tune of about 65%. One may wonder whether this value is significantly high. There are many reasons why this value is very high. One, the stress value of tethers move from yield to ultimate. So, this results or this initiates a plastic deformation in tethers. 2, if tethers are not designed to sustain that ultimate stress, it can result in what we call tether pull out, tether can come out of the structure. Most importantly, tethers are subjected to dynamic tension variation because of earthquakes. The moment I say dynamic tension variation is always not positive, can be negative also, the variation is there. Okay. This introduces additional fatigue in the tethers. And tethers can damage much faster than that of a traditional life or service life. And further, most importantly, the delta T naught variation happens in the vertical axis, because why? It is a taut moved system. Okay. Taut moved means it is always tight, vertical, and you all agree that TLP has got 6 degrees of freedom along x, y and z, where along z what we call heave, the displacement degree is considered generally to be a stiff degree. Why? The period of heave is from 2 to 5 seconds. When the period is larger, it is considered to be a stiff degree. Now, here is the catch. When the tension variation is superimposed on the vertical axis of the member, this will accelerate the heave degree, which is considered to be one of the stiff degrees of the platform. Now, this problem is similar to any structure which is resting on the ground, because the vertical motion of the seabed is triggering the structure as if the structure is directly resting on the seabed. It is happening exactly here same. So the stiff degree is triggered off because delta T variation. Where delta T varies means structure will be either pulled down or loosened up. It means heave degree is getting activated. When heave degree is getting activated, supposed to be stiff degree, this kind of behavior is not expected in a TLP. TLP is always designed to be complained only in surge, sway and yaw. It is always expected to remain stiff and rigid in heave, roll and pitch. But when this phenomena was noticed in the research saying that heave degree is getting triggered off, there is a very important outcome which makes this study very important. Now the question comes, how we can now mathematically model these forces on the TLP based on an incident available at Gulf of Mexico, because the question now comes, what spectrum will I suggest, because I want to analyze it. You cannot say I can do a simple case study on a TLP at Gulf of Mexico and adopt the same design phenomena for all TLPs anywhere in the world. There should be a spectrum which will govern me, like we have spectrum for ice load, we have spectrum for wind load, we have spectrum for wave load. We should have a spectrum which will define such incidents which can be used on a flexible system like a TLP or an articulate tower or a guide towers, etc. Okay. Now Kanei Tazimi developed a spectrum for this. The spectrum was suggested by Kanei Tazimi, called as KT spectrum. இன்னொரு 5 minutes ஆகும், extend பண்ணுங்க. Before that, let us see how this delta T is varying, delta T naught. This varies as a function of AE by L multiplied by x of t minus xg of t, where xg of t is called the ground displacement vector, which is nothing but x1 of g, x3 of g, and remaining all degrees are 0. It means it is considered in sway and the heave axis. Yeah, I mean the surge axis, surge and heave axis, sway axis is eliminated and there are no other axes at which the vector is considered. So I will call this equation number 2, 3. The one sided power spectral density function of the KT spectrum is given by equation number 4. You can see that it depends on 3 parameters. One is what is called S0, other is what is called omega g, and third one is zeta g. Omega g is called the ground frequency. This is taken as 2.5 hertz. Hertz. The reference can be Nigam, NC Nigam 1983. NC Nigam refers the ground frequency to be this value only when you apply this for a stiff system. Why we are using in this literature a stiff system? Because now, as I explained to you in the previous discussion, that delta T naught is directly superimposing the values of earthquake excitation on a stiff degree like heave. Therefore, it is as good as the structure is resting on the seabed under this delta T naught. Therefore, we have used 2.5 hertz as the ground frequency. Zeta g is called damping of the ground acceleration. Now, S naught is a spectral parameter which is given by this equation. Call this equation number 5. Where sigma g square is the variance of the ground acceleration. Now, the question comes, you must select the spectral value. What are the spectral dependence parameters? The spectrum or the kinetic energy spectrum depends on 3 parameters: S naught, omega g and zeta g. Omega g is 2.5 as applicable to a ground frequency for a fixed base, So, you must choose S naught and zeta g such a way that the generated spectrum should simulate a time history which is recorded at a specific site. So, it is an iterative scheme. Okay. So, what you have to know is what would be the measured acceleration and velocity at the specific site, and what would be the acceleration and velocity which I get from the spectrum. They should match. So, you have to simulate a signal in such a manner that the simulated velocity, that is x dot g, x double dot g, match with the recorded or observed x double dot g. That is one case. 2, it should also match at the maximum peak period at which the acceleration is maximum. So, it should not only match the signal amplitude, but also the time. Okay. So, seismic loads are not direct. Though you have a spectrum, the spectrum is depending on 3 parameters. You must select these parameters at random. Now, the question comes, how do you select these parameters? which can help me to simulate a signal which is matching with that of the value observed at site. Okay. Now the tool used, I should say, to simulate or to match the spectrum or time history signal to that of the observed values. Using statistical estimation process. Why statistical? S0 depends on the variance. Okay. Variance can be obtained only when you have got a statistical parameter. So it should be dependent upon statistical estimation process. So one can use any specific simulation available in the literature to generate a signal, check or generate the variance of the value, substitute S0, generate the signal, complete a time history and check the amplitude and the time or matching with that of the observed. Not matching, change the parameters, keep on doing it, iterative simulation. So detail of this is available in okay. So there are studies carried out by the researchers showing that how the earthquake loads can also be causing significant impact on flexible structures like TLP, which makes the study interesting and important for the offshore structures. We have got few more loads which are acting on the structural system. We will discuss in the next lecture along with the ultimate load design technique, which we will discuss in the next lecture.